All right, so one of the first places with it, we started to really think about the role of ribosome mass in hypertrophy is this idea that as we get older, our muscles, when we give them an extreme loading situation like this, so this is an example where what they've done is they've cut out the big calf muscle, the gastrocnemius, in mice, and they've let the plantaris muscle grow in response to the absence of the primary movers, the soleus and the gastrocnemius muscle. And so this increases muscle mass 70% in as little as 14 days. In the old animals, though, there's only a 40% increase. And so the idea here is maybe there's something in the old animals that is causing them to have limited muscle hypertrophy, whereas in the young muscle, you don't see that as much. So when these authors took a look at how much total RNA there was, and so the idea behind using total RNA as a marker for ribosome mass is that approximately 75 to 80% of all of the RNA within your cells are ribosomal RNAs. So when you look at the total amount of RNA per milligram of muscle, if you increase the amount of ribosomes, you should see, because that makes up 80% of all the total RNA, you should see a nice big increase in total RNA. And sure enough, within about 5 days of overload in the young, you see this really big, robust increase in total RNA concentration within the overloaded muscle. Whereas in the old muscle, you're seeing that the increase in RNA doesn't reach the same amount that you see, at least per milligram of tissue, that you see in the younger animals. And again, this is suggesting that older animals maybe don't grow their muscle as big because they have fewer ribosomes. So they don't have as many of the machines that are going to build protein. Similarly, the paper that I gave you for this week shows that in individuals who are non-responders to resistance exercise versus moderate versus extreme responders, if you look at 4 weeks out and you try and see how much total RNA there is per milligram of tissue, what you can see is that the bigger the hypertrophy response, so the extreme responders have the biggest increase in muscle mass, they also have the biggest increase in total RNA per milligram of tissue, which suggests that they have more ribosomes to build more protein. And sure enough, if you look after resistance exercise and ITS1, so the way that you make ribosomes is that the polymerase 1 binds to the ribosomal DNA promoter, and it drives the production of a very long piece of message, which is called the 47S ribosomal message. And then that's cut into pieces that contains the 18, the 20S, and the 5S ribosomes. And the ITS1 is an internal spacer. So it's basically intronic DNA that's cut out. And so this should only go up if you're actively making the whole construct, the whole 47S unit, because as soon as you cut it into the small pieces, those ITS sections are gotten rid of. Okay, so what you can see is if we look at this is the production of ribosomal RNA. Now you can see after resistance exercise, these filled circles, within 12 hours after resistance exercise, ITS1 begins to become significantly elevated. That precedes the increase in total RNA per milligram of tissue. So you don't see an increase statistically in total RNA per milligram of tissue until 36 hours. Whereas if you look out at the ITS1, you've got an increase already at 12 hours. The reason that this is different is because I told you that ribosomal RNA makes up 80% of the total RNA. So if you increase the production of ribosomal RNA, because there's already a big pool of it, it takes you a long time before you see a change in this. All right, I'll give you an example of this, an analogy here, is that if you have a little kiddie pool, like we used to have at our place where it's a little plastic pool, it doesn't fit much, you put a hose into it, and within about 10 minutes, the whole thing is filled. And you would have seen that the water level rose really quickly. We just finished building a beautiful new pool. It's a real pool. And so now we put our hose in it, we turn on the hose, and it didn't fill for over 24 hours because the pool is bigger. And the bigger the pool, the longer it takes before you see a change in the volume. So here, the pool of ITS1 is very low, so you start to see a change very early. Whereas the pool of total RNA is very big, and that takes longer before you see an increase in the volume. All right? So that's the first bit of data from here. The second thing is when you treat with rapamycin, what you can see is that you don't get the increase in ITS1, and you don't get the increase in total RNA. The interesting thing to remember here is that this is a relative. So this is all using the right leg that was exercised relative to the left leg that wasn't. The interesting thing that happens is if we look at this a little bit closer, that in the control leg, it's not that ITS1 is, so you can see that this is in the control leg, the unexercised leg. And so what you can see is that rapamycin is actually is bringing down the total amount in the control leg a whole lot more than in the vehicle treated. So when we say that there's a decrease or that there's an effect where ribosome biogenesis is lower in the rapamycin leg, we're actually seeing an effect in the control leg. So we're blocking ITS levels in both legs, and the exercise is actually bringing up the ITS levels to some degree in the rapamycin leg. Don't worry about that too much. What I want you to take is that ribosome mass is sensitive to rapamycin, that after exercise we see an acute increase in ITS1, which is the making of the ribosomal RNA, before we see an increase in the total RNA, in the total RNA. So how does this work? Well, we have either load or tension and or growth factors. Together with amino acids, we're activating mTOR, and that's going to be important for activating the existing ribosomes and then increasing the production of novel ribosomes. And that's where this increase in ribosomal mass is dependent on mTOR. So when we treat with rapamycin, we block ribosome biogenesis as a result of exercise. And so what we know is we need mTOR to increase ribosome mass, and we also know that mTOR increases the activity of the existing ribosomes. The thing with the ribosome mass is that we're going to regulate that in a couple of ways. One is through mTOR, and the other is through a number of other factors, including MYC and other things that I'll introduce to you later. Okay, so the first thing that happens that mTOR does is it makes more of these ribosomal proteins, the proteins that make up the ribosome. And the way that it does that is through the control of this protein that we've talked about before, LARP1. And what LARP1 does is it allows all of the ribosomal messenger RNAs, so all of the messenger RNAs that make up the 100 plus proteins that make up the ribosome, they all have what's called a 5' terminal terminal oligopyrimidine tract. So this is pyrimidines, are the G's and C's, and all of the proteins that make up the ribosome, they have a 5' mRNA that has lots of pyrimidines in it, because that makes it structurally more difficult to synthesize them, so you only make them when mTOR is highly active. Okay, so the first thing that mTOR does when you increase mTOR activity is it begins to translate more of these 5' top mRNAs into protein so that you can make more ribosome proteins, because you need both the 100 proteins as well as all of the ribosomal RNAs. So the first thing that you do after resistance exercise when you're activating translation through these suckers to activate existing ribosomes is now you're also going to translate more of the ribosomal RNAs into ribosomal proteins so that you're going to begin building more ribosomes.